Can we learn anything from the reversals of the sun?
Who wants to handle that question? I think they're very, very different, totally different objects.
The sun's field reverses fairly periodically, about 22 years. These things, it goes on for millions of years, well, thousands of years, and then suddenly reverses.
Yeah.
And it picks up a new polarity, and then it stays stable
Yeah.
for a long time, and then suddenly flips. So the time series is completely different.
Yeah.
With some models of reversal that should try to account for both that the information of the one loss of the ends. If you have a certain verification, you call back to the definition of the reversal in the reversal, Earth-like reversal, that sort of definition is Earth-like reversal.
Okay, let's try to last another 20 minutes. I'll start to talk about the inverse problem and how to make models of the magnetic field at the core surface. So we've talked about measurements. So the key thing here is that we want to take our measurements and use them to infer what is happening at the top of the generation region. So we haven't talked about the core, but the generation region for the Earth is the liquid core of iron, nickel, and a mixture of lighter elements, which is convecting. The inner core is a solid inner core, which is gradually crystallizing from the center, and that's the source of the field. Now, the mantle that surrounds the core is weakly conducting, and to a first approximation we can pretend that it's actually an insulating mantle. It's not quite right, but it's good enough for our purposes. And so this now means that if we say that the whole of the silicate mantle is an insulator, then we can actually use the solution to Laplace's equation not only where we make the measurements, but we can say that the same solution applies all the way through the mantle. So that's what we're going to talk about. Now, let's see where we're going to go. We don't really need that. That's just the normalization that we use. So I think I want to go quite fast here. Okay, the first thing to do is we know we have the spherical harmonics have got all these nice properties such as orthogonality with respect to one another when integrated over the sphere, and we also have this property that they are the eigenfunctions of the horizontal Laplacian, and we can use these properties to very rapidly get a result concerning the integrated squared radial field strength integrated over the Earth's surface. So if we just want to work out what the average squared radial field over the Earth's surface is, we can very rapidly get this result. And now in this section I've used beta LM. I've sort of switched because I find these GLMs and HLMs to be a bit awkward. So beta LM is either GLM or HLM, and you'll notice that actually I'm now starting to allow the M quantum number to become negative, just to save me a lot of writing. So we can look at what the let's see, we don't need all this. We can look at what the power spectrum looks like as a function of spherical harmonic degree, and this is what the power spectrum looks like as a function of spherical harmonic degree. You see that the field is strongest, of course, for L equals 1, which is the dipole, and gradually drops off to degree roughly 14, and then you'll see that it's fairly flat from then on. So we've got a power spectrum which seems to have two different components. Any thoughts on what the origin of that might be? I mean, one of these components is like is fairly white. It's like a white spectrum. White spectrum. sort of noise, shall we say. It's not actually the noise floor of the instruments. This is a real signal that actually originates with the magnetization of the crust. So what we see is that the field from the core gradually drops off in power until it reaches a point where it becomes overwhelmed by the power coming from the magnetization of the crust. So the only separation we can make between the field coming from the core and the field coming from the crust is actually really a spectral one. It's just based on its spectral signature. It's not based on anything else. So if we look at the signal in this portion, I think I've plotted that, we can actually deduce what the crustal field looks like. So this is now the I think this is the radial magnetic field plotted for spherical harmonics L greater than 14. So you will see, first of all, that you've got this this signal which is very much correlated with the distribution of the continents. So clearly the crustal field is stronger on the continents, including even here in Australia. It's stronger on the continents, and then in the ocean basins here it tends to be somewhat weak. And you can even see, it's very nice when you zoom in on some of these, you can even see how the crustal field is correlated with, I've plotted these lines, these grey lines are the lines of equal age because of seafloor spreading. So the crust is constantly being generated at the mid-ocean ridges. The oceans are opening up, and it tends to create magnetic stripes, and you can even see that. Admittedly, it's all very long wavelength, but you can actually see that in this model sometimes very nicely. So you see how these things follow the contours of equal age. It's quite convincing. So that's the first thing to notice, is how much stronger the magnetization of the continents is than the oceans. Yeah.
This over certain R, right?
Beg your pardon?
To get the spectral system, you are integrating it over a certain radius.
No, actually, all I'm doing, I'm simply doing it. No, I'm taking the Gauss representation of the magnetic field, but now I'm taking it out to something like spherical harmonic degree 160 or something like that. What is the
fixed parameter at which particular radius theta or pi?
This spectrum I'm showing you is at the Earth's surface. Yeah. And I'm just showing you that just to say that there's this change in the spectral content, and therefore what is done is to simply separate the field into two portions. If I throw away this section and just use this section and plot it, then I end up with an image like this. So this is just for spherical harmonics. L is 14 out to something like 150.
This is the image of the surface.
It's at the Earth's surface. Yeah. It's at that radius, 6371.2. Yeah. So it's purely based on. It's based on this spectral separation, but I mean, it's quite clear that it's largely correct, because you can see geologically how well correlated many of these signals are with the processes that are creating them. Okay, so that's the crustal field. I don't think I want to say anything much about that. So now let's do something here which I think is not often done, but I just want to show you the relationship between an observation at the Earth's surface and a core magnetic field. So a general magnetic field at the surface of the core. So we're interested in BR of theta phi here at the core surface, and if I make a measurement here at the Earth's surface, I want to know what the relationship between that measurement is and this core field. And it's going to turn out that this is the that there's a convolution, there's a sort of there's a blurring going on between the magnetic field here and the observation that you use to sense it. And there are a couple of these classic papers that work out the theory. So let's just start with some uniqueness results. Someone asked about boundary conditions before, and I neatly sidestepped the whole question. But the Dirichlet problem, which is this one: if you want to find a solution to Laplace's equation in V, and you give some boundary conditions on the potential on the boundary, then the solution is unique. In other words, it is sufficient to tell me what the potential should be on the boundary, and then I have a unique solution. That much is known. And the Neumann problem is the same one, but instead I don't give you the potential on the boundary, but I give you the gradient of the potential with respect to, or the normal gradient of the potential. And in that case, this problem is unique, but the potential is determined up to an additive constant. Now, that additive constant doesn't actually matter, because we're going to try to determine this potential, and then we are actually going to, of course, find the magnetic field. B is minus grad of, well, in this notation, grad of U. So even if U is determined up to an additive constant, as soon as we take the gradient, that additive constant disappears. So both of these problems are essentially unique for our purposes. So that much is known mathematically. And the last thing I want to show before we just stop for T is what is the relationship between a component, an observation on the Earth's surface, and the core magnetic field. So it's known that you can write the potential V as a convolution of its gradient on the boundary, BR, with a certain kernel here, or a certain Green's function, G. And we need to find that Green's function. And we'll do that very quickly. So, well, perhaps we don't want to go through every step on here. I'll let you look at this later. You can use the orthogonality of the spherical harmonics to show how one of these spherical harmonic coefficients is related to the radial field at the core surface, and therefore you can just stick everything back into the expression and find how the potential is related to the magnetic field at the core surface. Yeah.
So if there are strong currents and core, how is this justifying?
You asked about currents.
Currents in the core, and we are using this.
Yeah. No. So I only want to solve for the potential either above the surface or in the mantle, and I certainly don't want to go any further than this boundary. So I'm just going to solve in this region, and I'm going to try to relate an observation to the magnetic field, which is so BR here is equal to minus dV by dr. That's right. So I'm going to make a relation between V and its gradient measured on that boundary. And that's what I've got here. I've got that V is related to its gradient measured on that boundary. So in this section, r hat is simply the unit vector, which is describing your position on the surface of the core. So we're actually almost there. We just we've got a big sum over lots of spherical harmonics, and you can imagine that if you use the addition theorem, you can actually collapse this big sum. I won't go through all the details, it's written down here. This is the Green's function you want. It's a big sum, an infinite sum over this sort of product of spherical harmonics. And if you use the addition theorem, you can find that you can write this kernel in closed form. So this all comes from the classic papers of Gubbins and Roberts, I suppose. What I want to do is to plot this and just show you how this is useful. So if I make a measurement of the vertical field at the Earth's surface, how much sensitivity do I have to the radial core magnetic field as a function of distance from where I am? So there's a point immediately beneath my feet, but I'm actually able to sense the core magnetic field a distance away from me, an angular distance away from me, and this is the kernel that tells you how to do it. So this is the kernel that sits in that convolution. So those of you who know about astronomy, this is essentially the point spread function of the telescope. Yeah. And the interesting thing is that you have sensitivity. Obviously, you have the most sensitivity to the magnetic field immediately beneath your feet, but you have sensitivity all the way out to the antipode. So even if you have a magnetic field line emanating from the core at the antipode, you have some sensitivity in your measurement to that magnetic field line. And this thing is rotationally invariant with respect to your observation site. So I'm sorry there's no scale on here, but this is mu is the angular distance away, so this is 0, this is 180 degrees away. Now the consequence of this is really the following. If you, I mean, there are many inverse problems where you your ability to discover the field that you're interested in is limited simply to making the measurements in the vicinity. So imagine that we want to discover the magnetic field just in the garden. The best way to do it is to go and make a survey in the garden. But the strange thing about having this very broad point spread function is that you can actually make a measurement on one side of the globe, and you're sensitive to the core field on the, as it were, the other side of the globe. So the reason this is important is that we're going to be looking at some rather heterogeneous distributions of data, but the key thing is that each datum that you collect at the Earth's surface does have some sensitivity to the core field everywhere, right? And the problem that you're going to solve is a deconvolution problem with this particular point spread function. It's this particular one if you make a measurement of Z. It's a different one, let's say if you make a measurement of declination, then it's much more complicated. But essentially you still have some sensitivity to the field a long, long way away from you on the core surface. I don't know if that's understandable. If it's not, come and ask me at tea time, because I think it's a good place to stop. But that's the basic idea, that you have some sensitivity to the core field from all your observations. Okay, so we stop there and let's take tea.